Hey, this is Horner, and this is Circuits F3, or the free response for the review. We have an ideal battery, EMF, and I know we haven't really talked much about that, so let's talk about what this is. A battery has something called electromotive force, and that is what pushes, quote unquote, pushes the electrons out of the battery. So here we've got electrons flowing in this direction, and then we have current that flows in the opposite direction. That's what we're used to thinking about, is that current flowing through. So when you have a battery, we talk about EMF. When you have voltage or potential difference is really what this is. That is from one side of a circuit element like a resistor or a bulb to the other side, and that's the voltage drop. So when we talked about voltage drop, that's potential difference. This is what we call a variable resistor, and so they've drawn that. This is one that you can change the resistance by turning a knob. And a voltmeter is initially connected right here. They want us to write some expressions in terms of the potential, in terms of EMF, R and R. So notice that we're not going to use capital V in our answers. The current that passes through the battery, we know that by Ohm's law, I is equal to voltage over the total resistance. But in this one, we have to substitute in our E for our battery, okay? And we have to substitute in R plus little r for total resistance. So that one is pretty simple. The next one's a little bit more difficult. This is our answer. Where did it come from? The meter measures potential difference just for this resistor. So we're going to say that's equal to big I, the current flowing through the resistor, times little r, which is the resistance of that variable resistor at any point in time. For the circuit, I is equal to the EMF of the battery divided by the total resistance, which we know is this equation. So at this point, we know that both of these get full current. If that's correct, we can substitute in, using the blue line, our expression for I, which is right here. And when we do that right here, notice that we get EMF times R. And so follow the green lines. There's EMF times R. And then on the bottom, we have big R plus little r. Be careful, you cannot cross off the r's here because you don't have a little r here, and that's why. So that is part I and part double I. That is 4 total points right there. Now you have a student constructing a graph of V versus R. So it shows big V versus R. And when they do that, we're going to use EMF in the battery. So we're going to use E, and we're going to use capital R here. So they want to know which aspects of the student's reasoning when you read this. So it says Ohm's law says V is equal to IR, then delta V and R are directly proportional. Now, here's something else that you need to know the difference between. If I have a straight line, okay, but it doesn't go through the origin, we said, and we've always said, that that is linear. If you have something that is linear and it also goes through 0, 0, that is called a direct proportion, and I like to use dp. And you need to separate the two because here it says directly proportional graphs are lines through the origin, which is 100% correct. This one is not directly proportional, but it is linear. So that is the difference between those two things. So let's go ahead and tell what kinds of things here about the graph that the student said that are correct. So here, series resistors have the same current. That is correct. So in a series circuit, we do have the same resistance all the way, we have the same current all the way through. So if this one has got 2 ohms, this one has to have 2 ohms also. Second thing, delta V and R are proportional if I is constant. And that is correct. It is directly proportional. We forgot the word directly here, so I'll add a little d there. Are directly proportional if I is constant. That's right. Directly proportional does mean that it goes through 0. So those 3 aspects are correct. The thing that is wrong is they said that the current stays the same. And as your R changes, notice as this number changes, that will change the current. So I would also include here that I is equal to the EMF over R plus R, and if little r changes, so does I. And you can reference this equation to show that. That's one point. Now they wanted us to sketch a graph here of the reading of the voltmeter as a function of the resistance R. So as I am increasing little r, I also increase my total resistance. So here we're going to draw our line. It starts at E, okay, because remember that's the voltage in the battery. You don't have anything bigger than that. So that's where it has to start. So don't start it like, remember here, we're just showing the proportionality. We're not going through and actually taking data. So here we are taking data and we have to start at E. This one will always slope down, so as long as it slopes down, it's good. As long as it passes through 1/2 E and R, then we're good. And finally, it's always concave up. So I'm actually going to go back and I'm going to redraw this. So I'm going to erase it so that you can see that concavity, I guess. So any term you want to use there. But let's draw it so it's a little bit more concave. So we're going to start it and kind of make it up here a little bit, and then we can kind of finish it out. And it should kind of look like that. So now I feel like that's a little bit more concave, and this is the point that it needs to go through for sure, 1/2 E and R. So notice I actually started there and went this way and started there and went this way to make sure I did that. And that is the end of this little bit longer 12-point problem.